السلام عليكم. آه، رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني ويفقهوا قولي ربي زدني علما. I apologize for my last presentation and for my last, it was a bit noisy. I was under a lot of stress for time limitations. I hope you can understand whatever I was speaking. The topic I was discussing was friction, and if there is a slight, let me put it this way, uh, noises, background noises, I apologize for that. But now, the most of the material that was discussed is from your book. You can open your book as a part of educational process. Do open your books, and let's move on. We are going to talk about the examples related to our previous discussion. Let me just fix the door first. There's a lot of noise and hammering going on. 1 minute. Welcome back. Now, this is a very basic numerical problem based on frictional analysis. If you are, if you have went back to your room after taking the previous video lecture, so-called, and studied some of the first few pages of chapter 6 of Merriam, 9th edition, you would have gained certain concept about friction. So let us look at this example. Determine the maximum angle theta which the adjustable incline may have with the horizontal before the block mass M begins to slip. Now this is interesting. The coefficient of static friction between block and inclined surface is mu s. So what is the maximum angle? Now this is again what you will get is the angle of friction, which we have studied in, I think, second last article of the article. How are you going to find this thing? As you know, mass under the gravitational force field is going to act as a value, generate a value g. Where is the mouse? There it is. Right like this, mg. Since this mass is this weight under gravitational force is working horizontally down, vertically down to the center of the earth, then there is going to be a reaction force generated by this plank outward. This reaction force is going to be balanced by a component of this mass mg weight downwards and another vector component acting this way. So this is going to be your angle theta. So here angle theta would be defined as mg cos of theta, which is going to be equal and opposite to the normal force, and mg sin theta, that would be equal and opposite to force F. So since our mass has not slipped, so we are going to say it has reached the maximum limit, so mu s is going to be maximum, and for that case we are going to balance all the forces along x-axis and all the forces along y-axis equal to 0. So we come back to our old habit. It is everything is static, so everything is 0, and what you get is mg sin theta minus f is equal to 0. Mg minus mg cos theta plus n is 0. Why minus signs are conventions? Here, like a universal design for every diagram, you need to represent your legends. Where is the x positive, where is y positive? And finally he came across these equations. So taking these two equations are very important. So sine by cos, you get tan theta, and what you get is f over n, and this is what your equation is. So we say f is equal to mu s times normal. As discussed before, mu s is defined as tan of theta, or in the book he has said tan of phi. So this is a very, let me put one more very simple numerical. Hope you can do it. Let's go to next one. Wow. The next one is a very interesting numerical. So let us discuss this numerical. The three flat blocks are positioned at 30 degrees inclined as shown in the figure. and a force P parallel to the inclined plate, incline is applied in the middle block. The upper block is prevented from moving by a wire which is attached to a fixed support. The coefficient of static friction for each of the three pairs of the mating surface is shown. You can see mu s for upper and the bottom, that is 30 kg to 50 kg is zero point 0.3, and from 50 to 40 kg is 0.4. Determine the maximum value which P may have before slipping may take place. So consider this thing at an equilibrium. Considering both the cases are at the top positions, you got first you're going to analyze step by step. The first thing is you're going to balance 30 with 50, and you're going to say they have achieved an equilibrium. The tension T will equally be balanced by the F1 force times the weight. So the equation for the upper portion would be two types, right? For the tension force. And then once you have solved for the upper portion, then you're going to solve for the bottom portion. That is mu s is equal to 0.4. So you have to remember the normal force for the downward force is going to add up simultaneously. For instance, for 30 kg, let's suppose this is the center of mass acting here, 50 kg center of mass acting right here, 40 kg center of mass acting right here. Each time a normal force is going to generate equal and opposite. A normal force is going to be transferred here. So you're going to first balance this point, then you're going to balance this point, and the reaction forces of this point is going to transmit to these points also. So you have to add these points together. As you can see in this case right here, they have been introduced. Isn't that amazing? For this force being introduced right here and this being introduced right here. And then you are going to say F1 is equal to F2, F is equal to mu n, and then some are going to say sum of all forces. The universal truth for equilibrium is sum of all forces along x equal to 0, sum of all forces along y equal to 0, and hence you can easily solve, for which you are going to find the value of P, which is right here. That is 93 newtons. Wow. So that much, only this much force. How easy was that? This is again a part of your book. You can solve it. If you have any problems, do discuss with me. Thank you. This would be all for today.